Welcome to our webinar on the groundbreaking co2 project. Launched in March 2022, the co2 project set out to revolutionize the modelling of CO2 journeys, seamlessly integrating the process from its delivery point to subsurface storage. By bridging the gap between injection and storage, the project achieved a significant milestone, connecting Kongsberg Digital's ledaflow transient well and pipe modelling software with CMG's GEM reservoir simulation software. Thanks to the collaboration between Kongsberg Digital, CMG, and a dedicated group of companies, we have developed a solution to a critical industry challenge, ensuring the safe injection of captured CO2 into storage sites. CO2 Link is the first coupling of a standalone commercial multi-phase flow simulator with a reservoir simulator, specifically designed to address CO2 transport and injection. This capability marks a significant advancement in our understanding and reduces the risk of failure in CO2 storage. Join us as we explore the details of this innovative solution and its impact on the future of CO2 storage and sustainability. Our speakers today will be Wouter, Senior Principal Engineer at Kongsberg Digital, and Reza, Senior Reservoir Simulation Engineer. If you have any questions, please do share them in the chat and we will try to answer as many as we can in the Q&A at the end. So, without further ado, the stage is yours, Wouter.
Thank you, Michelle, for the introduction. There we go. So, oh, that was a bit too fast. There we go. So the content of this presentation, oh, there's a bit of a delay. Yes, hopefully it stays on this slide now. So the contents of this presentation are as follows. So first of all, I will give a bit of an introduction about the project and why we are interested in coupling ledaflow and GEM. Then the coupling concept. So looking at the technical details of the implementation and some of the concepts surrounding this. Then I will go through what is ledaflow and what are the special features in this simulator. And Reza will take over with a presentation of what GEM is all about and give a demonstration of the products. So in terms of introduction, so this is basically the overall strategy that we have in order to do simulations of CCS. So first of all, on the left, there's the capture process. So that could be any kind of CO2 source really. So it could be chemical industry, oil and gas production, maybe even waste incineration. So that there you can model the capturing process using K-Spice, which is a Kongsberg product. So where you can simulate the process. Then ledaflow can be used in order to simulate the transport process in the pipelines. And finally, we get to the storage part, where you have both ledaflow for simulating the wellbore, as well as GEM for simulating the reservoir. So that's basically the overarching vision that we have for CCS, where you can combine not one, not two, but maybe even three simulators to simulate the entire dynamic process as a coupled simulator. Then the coupling concept, the software architecture is as follows. So what we have done in the co2 JRP, which is an R&D project with 12 industry partners, is to develop a controller application that combines the two simulators. So essentially what it does is alternatively, it runs ledaflow and GEM. So you have the controller application that sits on top and makes sure that everything is synchronized and that the data gets exchanged. and then it runs the GEM simulator, which has its own file storage, and also it runs the ledaflow simulator, which stores its data in a database, and those two work together through the controller. The controller not only exchanges the input and output information from GEM and ledaflow, but it also makes sure it implements a handshake time step. So this is the overall time step for exchanging information between the simulators. And in addition, both simulators, they also have their own internal numerical time stepping. And the controller also supports fast forwarding ledaflow in case you're running a very long simulation in GEM, maybe for several years time horizon. Then it's possible to, for periods of time, to turn off ledaflow, so you don't have to simulate all the time. And this leads to quite a saving in calculation time. Then continuing on the coupling concept. So of course, the most central part of this is the variable exchange between the simulators. So the coupling, it supports both injection as well as production from the reservoir. So the physics in the simulator, they determine naturally whether or not there is injection and or production. So it also can change during a time interval. And some of the inputs to the simulator, it will not be used depending on the state of the model. And I will come back to that later. So in the pictures that I've shown here, we see the GEM domain, which consists of mainly the formation and also a small part of the wellbore where the bottom hole pressure is defined. And then the ledaflow domain, it consists of it doesn't really simulate the formation, that is handled in terms of an IPR. But ledaflow has a very detailed discretization of the wellbore, where we define the wellhead pressure at the top and the bottom hole pressure, temperature, and composition at the bottom. And so those define the different variables. And the input to ledaflow, it comes as output from GEM. So that in this case, it involves an IPR table, which means the mass flow rate versus the bottom hole pressure as a table. And we have one IPR table for the injection, one IPR table for the production, so that is redundant depending on whether you're producing or injecting, but it's important to have both just in case the physics decide to reverse the flow. Then also the composition and temperature are specified as input to ledaflow. This is only used in case there is production. Then the opposite, the output from ledaflow equals the input to the GEM simulator. In this case, that is the mass flow rates through the perforations, and the composition and temperature. Those are used in case there is injection. So that means most of the time, the composition and temperature at the bottom hole conditions, they are transferred from ledaflow to GEM when we're injecting CO2 into the reservoir. So that is the most important part. And continuing on towards the description of the ledaflow simulator. So ledaflow is a 1D advanced transient multi-phase flow simulator. So that's a lot of different terms. But essentially what we use this for is to simulate from the wellbore sand phase to the processing facilities. So essentially that means both wells and flow lines can be simulated with ledaflow. And we are interested in the multi-phase flow behavior, and the simulator is dynamic. The ledaflow is based on models that are closer to the actual physics of multi-phase flow and provide a step change in accuracy and detail. So we do that through a set of mechanistic models to simulate the multi-phase flow. And we also have some special features like ledaflow slug capturing, which predicts and resolves hydrodynamic slugging. The energy equations in ledaflow, they're solved for each continuous phase. So that means that we have different temperatures for the oil, water, and gas phases. And each of the 9 fields, both the continuous as well as dispersed, they have their own mass equation. So we're solving things like droplet entrainment, bubble entrainment, oil-water dispersion. We can solve that in great detail, and we have full control over all of those at the same time. Then ledaflow is used by multiple disciplines. So not only flow assurance engineers. They're used by production engineers, people working with CCS. So we have many different kinds of users that use it throughout the project lifecycle for things like gas liquid management, thermal calculations, solid and integrity management. You can do lots of interesting things with ledaflow. And to elaborate a bit on that, the application areas for ledaflow, they include the classic flow assurance engineering. That's where it all originated as far as ledaflow is concerned. But we've been doing production engineering for many, many years already. You can use ledaflow for well kill analyses, where we first model the well blowout and then the subsequent kill operation using drilling mud. And you can use ledaflow together with K-Spice as a coupled simulator for dynamic field simulators, operator training simulators, real-time flow assurance, and virtual flow metering. And you can do all of those things for oil and gas, as well as CO2 transport and injection. Then ledaflow for wells. So this shows some of the typical scenarios that you can simulate using ledaflow. So in ledaflow, you can build a quite detailed well model using not only modeling the flow inside the tubing, but also you can model flow inside multiple annular spaces around the tubing. So you can use that for gas lift, but also for well integrity management, looking at the pressure in the different annular spaces as the well heats up and cools down. And then you can do different scenarios like well cleanup, warm up. You can look at slugging, artificial lift, and many other flow assurance disciplines like hydrates and wax. And all of those scenarios we can simulate all the way from concept selection all the way to the operation stage.
Thank you, Wouter, for that introduction on the ledaflow and controller. Let me now talk about GEM, and let's after that we look at the a live demo session of the the controller interface. So in CMG, GEM is known as the multi-dimensional multi-phase compositional simulator, which using either Penn-Robinson or SRK equation of a state in order to predict the phase equilibrium compositions and densities. In our GEM thermal simulator, we solve a number of equations to solve the system. And those equations would be the volume constraint equation, the set of the volume of the fluids, which needs to be equal to the pore volume of the system. And then the component flow equations, which are practically the material balance equations for oil, gas, and water components. We also solve the energy balance equation to include the effects of the convection, conduction, and heat losses. And of course, we have the phase equilibrium equations also in GEM simulator. Based on that kind of being a multi-phase compositional simulator, we have used GEM to model the many applications. It has been used to model the unconventional resources. It can be used to model the advanced process EOR techniques, such as chemical EORs, low water salinity injection, in order to evaluate and optimize those operations. And with respect to this, the energy transition area, GEM has been a tool to not only for CCS process, but also for other applications like geothermal, hydrogen storage, etc. Now focusing on mainly the CCS in here, there are a number of functionalities available in GEM that makes it a kind of suitable tool in order to model the CO2 geological storage. With those features, we can model the all the kind of possible CO2 trapping mechanisms under the in the underground formations. On the fluid side, We can do the CO2 solubility in the aqueous phase. We can also model the H2 vaporization, and you can also model all the geochemistry reactions inside the aqueous and any other mineral reactions between the rock and fluid. The Joule-Thomson effect is included in the thermal option of the GEM. And on the residual gas trapping mechanisms, you can model the relative permeability hysteresis effect. And finally, on the geomechanics, you can model the integrity of your cap rock, any possibility of the thermal fracturing or fault reactivation during the injection of the CO2 into the formation. So about the communication between the GEM and ledaflow, how that communication is happening, we typically look at the bottom hole location in here when you would try to couple your perforated interval in the GEM model with the well device zone that you have in the ledaflow wellbore model. In that communication, what happens is that actually at time 0, GEM initializes the model and generates the first IPR information. And that IPR information will be passed to ledaflow to march to the first time step. When ledaflow converges to the solution, typically the mass rate injection, the bottom hole injection temperature, this information would be now passed back to GEM, and GEM will take this information as a kind of operational constraint required for the simulation in GEM. And then GEM would march to the first time step and generates the IPR at the end of that time step, which will be passed to ledaflow for the next time step. And this sequential process would be continued until the end of the simulation. So now with that kind of introduction, let's go and then look at a kind of demo example that we prepared for this webinar. Here I am showing the typical GEM model in here in our preprocessor builder. The assumption is that we have already prepared a GEM model and ledaflow. Here is the location of my well in this depleted gas formation example. And in the cross-sectional view, you can see the perforated interval from top to the bottom, and also the local grid refinement around the wellbore in order to increase the resolution and accuracy of the results. Now in ledaflow interface, you can see our wellbore model, a vertical well from top to the bottom. And in the tubing in that wellbore model, we have placed a choke at the wellhead to open and close the well, and also a well device at the bottom of the well, which is a key position for exchanging that information between ledaflow and GEM. Before we start the coupling process, usually between ledaflow and GEM, we need to initialize the ledaflow model by this option. And then when we initialize, we just need to make sure that the status of the ledaflow has been set to the initialized, as you can see from here. And then our ledaflow model would be ready for the coupling process. Now let's look at the main GUI of the controller. This is what you see in the beginning, and then you can start with the Neo case by coupling your ledaflow and GEM models. On the left-hand side, we've got a couple of sections that user needs to provide information on that. In the first step, we add our models. Let's add the CMG model. And then via the settings, we need to make sure we are using the correct version GEM to do the coupling. Here, you can also change the CPU to run the GEM simulation with the higher CPU if that's needed. And then we add the ledaflow model from the available models in the list. This is the model that we just initialized now. There is a case ID information next to it that can be checked with the case ID information in ledaflow interface, just for checking the consistency of what we are importing in the controller. In the next step, we couple the wells. If the name of the wells are the same, you just see automatically controller has been coupled them together. If that's not the case, we pair them via this option. You select the wells and then we click OK. Then we go to the controller, and before we run the simulation, we save as the project with a name. And after this process, we would be able to run the simulation. We need to decide about the time step sizing in here. The first approach would be either a fixed time step size throughout the simulation and defining the number of the time step that we want to have, and then the coupling duration will be calculated automatically. But there is also another option, quite advanced, which we call it variable controller time settings. And with that option, you would be able to define a different time step size throughout the simulation. Like in this example, we will be using a 20-second time step size in the beginning when the transient effects are very important to be captured for us in this example. And towards the simulation, when we move to the pseudo steady state, we will be using larger time step in the simulation. And then you will see the coupling duration automatically calculated by the controller. Now everything is ready, and then we can hit the run button. And after that, you will see two log windows opening in here. The top one will be for running GEM simulator, and the bottom one would be for the ledaflow model. As you can see, ledaflow is now progressing with the simulation, which will be based on the initial IPR model that has acquired from the GEM simulator. So based on that, it will march to the 20 seconds, the first time step, to converge to the solution. And when that information would be available, it would be passed to GEM. And now GEM will take that information to march to the first time step of that 20 seconds. So as you can see now in here, GEM is now running by taking the time step. While the simulation from both tools are progressing, you can also have a look at the results at the same time. There are four main results available in the controller: the gas rate injection, the well bottom hole pressure calculated by two applications, both ledaflow and GEM, and well block pressure, which would be the pressure at the top perforated block by default in your GEM model, and then the temperature of the bottom hole, the injection temperature at the bottom hole. It is worth to mention that the controller comes with a documentation in which you will have a kind of quick start kind of steps and the workflow of how to use the controller and do the coupling process. We also provide in the template folder a number of examples. In each folder, you would see a different, a kind of separate ledaflow model and GEM model that you can couple them together and explore them. And that would be achievable by using the latest commercial release of the GEM and ledaflow for that coupling process. So now let me show you the final results of the demo in the next two slides. This is the well bottom hole pressure on the left-hand side, the quite increase on the pressure as we would maintain the injection rate of the 2 million cubic meters per day in this well. The top hole condition at the well head was about 4 degrees centigrade and 40 bar, which represents a kind of typical CO2 liquid injection. And then on the right-hand side, you will be looking at the well bottom hole pressure, well bottom hole temperature, which is quite a low temperature at the bottom hole due to that cold temperature injection at the wellhead. We can look at the results inside the wellbore from the ledaflow side. Here you can see the start of the CO2 liquid phase injection at the top to the wellbore, which was initially saturated with the CO2 gas. The liquid is kind of injecting down towards the wellbore, and at the same time you can also see the changes of the pressure across the wellbore. Other parameters like temperature, velocities can also be visualized in ledaflow. And then when we look at our kind of reservoir gem model, we can see that across the wellbore from top to the bottom, which was perforated, we are pressurizing by injecting that CO2, and you see the CO2 plume migration towards the reservoir grid blocks. And because we are quite injecting with very cold CO2, you will see quite low temperature in the grids near the wellbore area, which at the end you might start to see the kind of buildup of some CO2 liquid around the wellbore. So with that, we come to the end of this webinar. Thank you for attending our webinar.